this section of determinants. So in the last video we said that we could compute the inverse of a matrix, okay, that is if the inverse exists, by getting the matrix of cofactors. We transpose it and then multiply it times 1 over the determinant of A. And we say that the determinant of A can be or computed by taking cofactor expansion along in a particular row or column. And then we gave this short form the adjugate, okay, some people call it the adjoint of A, okay, that is the the cofactor matrix transpose is the adjugate, okay, or the adjoint, which is, you know, written in short form like this, and then times 1 over the determinant. Okay, so for now we would like to look at what they call Cramer's rule. Okay, Cramer's rule, I won't go so much into the details, but it closely follows from, you know, these ideas here, or rather these ideas actually closely follow from Cramer's rule. But what does Cramer's rule tell us? It tells us that in a non-singular system, remember we said if the system is non-singular, it implies that the inverse exists. Okay, so we say Cramer's rule says that in a non-singular system, A, okay, times x, of course this is of how many, yeah, n by 1 equals to b, and we know that b is also n by 1. Okay, the ith unknown, or the ith unknown, i.e. xi, okay, is given as the determinant of ai, okay, times 1 over the determinant of a, where ai, okay, ai is identical to a, okay, except that the ith column of a is replaced by b, the right hand vector. Okay, so we get the ith column of a and then we replace it with b. In other words, if you want to find x2, then x2 is going to be the determinant of a2 over the determinant of a. A is this one here which we have, but then a2 is that where we have, okay, the columns of a, I mean the second column of a, column number 2, that is a, all rows, second column. In other words, this column here is deleted, okay, and then replaced with the right hand vector b. Alright, okay, let us look at an example here. So we have an example, and what does it say? The example says that to determine the value of t, we want to determine the value of t for which x3 of t, okay, the solution here is in terms of t, now that's a function of t, is minimized. We want to find the value of t for which the, you know, x3, that is the vector in the third position here, is minimized. Okay, so we have our matrix A, okay, given as that, and then we have 0, t, we have t squared, and then we have 1, we have t squared, and t to the power 3. Okay, and then we have of course it is x1 here, and then x2, and then x3. Okay, and then we have the right hand vector b, which is giving us 1 over t, and then 1 out of t squared. Okay, this is in the form a x, but this is x of t equals to b. We can write b of t if you want, and so on. Anyway, so but we want x3 of t, but from Cramer's rule, okay, why are we going to use Cramer's rule? We only want x3 of t. Of course, this one here has we have x1, x2, and x3 of t as our solution. Why? Because a is over 3 by 3, this is 3 by 1, and b here, okay, no, we don't know this, but we know this is 3 by 1, therefore we know this also has to be 3 by 1, because we know if the number of columns here equal to the number of rows, then the solution is going to be 3 by 1, which we have here. So we know that this is a 3 by 1, in other words x1, x2, x3. However, since this only want x3 of t, there is no need to compute x2 and x1, therefore we use Cramer's rule here. And Cramer's rule tells us that to obtain x3 of t, we shall simply say it is going to be the determinant of a3 divided by the determinant of a. And what is a3? a3 is going to be identical to a, but with the third column replaced with b. So we have this t0 1, and then we have 0 t squared, but then this whole column is replaced with the right hand vector, which is 1 over t, and 1 over t squared. And so that is that. So maybe one trick I didn't tell you last time is that in cofactor expansion, it is always efficient to use the one which contains quite a number of zeros. So for this one here, we shall just use cofactor expansion along maybe the first row here, perhaps. So if we deal with cofactor expansion along the first row, so we are going to go straight away, do two things at a go: get the entry and then multiply it with its cofactor. So we have the entry, the first entry here is t, okay, and then we multiply it with -1 to the power 1 plus 1, because this is 1 1, this is 1 2, and this is in position 1 3. So I'll just say 1 plus 1 and then say add 2, and then what is the minor, the determinant of the submatrix, after the determinant of the submatrix which remains after deleting the row 1 and deleting its row and deleting its column. So here we have t 1 out of t squared, 1 out of t squared, then plus, of course this is good, it's a 0 multiplied by anything is going to be 0, then plus we have a 1, then multiply by -1 to the power 1 plus 3, which is 4, then times the determinant of the submatrix after deleting this row and its column. So we have 0 t 1 and t squared. Okay, so what do we have? We have t we have that is positive 1, and then we have t times 1 over t squared is going to be 1 over t minus is this, yes, minus 1 over t minus t. Okay, this is t over t squared is 1 over t, and then t squared over t is t, and then plus this is also 1. Okay, this is 1, and then this is also 1, and then we have this is 0, and then minus t. Okay, so this is going to be t multiplied by, what do we have? We have t, we have 1, and then minus t squared, and then plus the whole of this gives us negative t. So what do we have? We have 1 minus t squared, so we have 1 minus t squared minus t. Hopefully, if I haven't made any error. Okay, yes, and then this is what have we been computing here? We have been computing the determinant of A3. We have been computing the determinant of A3. Okay, therefore the determinant of A3 is that. Okay, please allow me to tell you, okay, what I see in the book here, that the determinant of A, let's see, the determinant of A is simply -1. Please verify. Okay, verify that the determinant of A, which we can write as determinant of A, is -1. Okay, for purposes of time I will just write what I see in the textbook here, such that x3 of t is simply determinant of A3 over determinant of A, and which we have as 1 minus t squared divided by -1, for which t becomes positive, and then that becomes positive, and then this becomes negative. Okay, so when they say we want to find the value for which x3 of t is minimized, of course they want you to find the value for which the value of t for which this is equals to 0, and I know you can be able to find this out. Plus t minus 1 equals to 0, for which of course we see that 2t plus 1 is equals to 0, and therefore x3 of t is minimized at the value -1/2. Okay, so yeah,